Advanced features. Arrays. You can declare arrays in the code component. These act as buffers that you can use for storing past values, for example, or for using as a lookup table. An array is declared as follows. Float buffer 100. This defines an array called buffer which is 100 floats, 4x100 equals 400 bytes, in size. Initializing. By default, all the entries in the array are set to 0. You have two other options for initializing an array. 1. Set all entries to a particular value. Float buffer 100 equals 0.62. 2. Randomize the contents of the array. Float buffer 100 equals rand minus 0.5, 0.5. Accessing. To access a particular entry in an array, use the array specifiers, square brackets, out equals buffer 25. Buffer 6 equals 3.14159. Note that the array index is 0 based, so in the example above, buffer 0 would be the first entry, and buffer 99 would be the last entry in the array. You must make sure that you use indexes that are within range for the array. Failure to do so will produce unpredictable results and could even crash the software. Hop. There are some calculations that don't need to be calculated for every sample. It's sufficient to recalculate for every fourth sample, say. For this purpose, we have the hop command. The syntax for the hop command is as follows. Hop 8. Code in here is executed only for every 8th sample. Hops must be powers of 2 and the maximum hop length is 4096, so values of 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048 and 4096 are the only acceptable values. Loop. Sometimes you need to execute the same code several times, changing one or two parameters on each pass. You can do this in the code component using the loop command. Here's the syntax. Loop 10. Code in here is executed 10 times in succession. You could use a loop to initialize an array, for example. Float index. Float buffer 10. Loop 10 buffer 10 equals syn1 index. Index equals index plus 0.1. You should take care not to use too many loops, or loops with many iterations, as they can cause significant increases in CPU. Also, for some loops, like the array initialization example, you only want them to be executed once. This is where the stages come in. Stages. The code is split into two parts called stages. Stage 0 runs only for the first sample, but stage 1 runs for every sample. For the example we've just been looking at, we could put the array initialization into stage 0, and it will run only once. Defining the stage is very easy. Stage 0. Code in here is executed only for the first sample. Stage 1. Code in here is executed for every sample, including the first. Any code written outside of the stage definition is assumed to be stage 1. Special stages. There are in fact two additional stages, stage 2 and stage 3. These are only used for implementing delays. They are needed to make sure that data flows correctly when one or more delays are chained together. The software executes the code in stage order, so stage 1 goes first. For a delay, stage 1 isn't needed though. Next, stage 2 is executed. Stage 2 is used to move data from the inputs to internal variables, most likely a buffer. Each stage is executed for the whole of the schematic before proceeding to the next stage. Stage 3 is used to move data from internal variables, again, most likely a buffer, and the outputs. An example of how to use stage 2 and 3 for a delay is shown below. Stream in, stream out, stream in delay, float mem 44100, float index, Stage 2, mem, index, equals in. Stage 3, index equals index plus 1. Index equals index. Delay and index. Out equals mem, index. Debugging. Using syntax coloring. We've already seen that the first indication you will have that your code is incorrect will be a discontinuity in the syntax coloring. The following example shows this. You can see that the coloring stops with the syn function. This indicates that there is something wrong with the expression. Sure enough, we forgot the 1. The line should read A equals syn1 in. If we make this correction, everything becomes colored correctly. Checking the assembler. The code component converts the high-level language that it uses into x86 assembler prior to compiling. You can look at this assembler code by connecting a text component to the string output of the code component. If you understand assembler, and even if you don't, it can be useful to examine this code to make sure that nothing out of place is happening. When there is a syntax error, the assembler code will only be generated up to the point at which the syntax broke down. If the syntax is correct, then the other possible problem could be the limitation on expressions discussed earlier. This is much more difficult to spot in the code, because the coloring will indicate correct syntax. However, a quick look at the assembler code can identify this type of problem. The example below shows exactly this. The way to spot the problem is to look for XMM 999 in the code. If this happens, then you know to look at your expressions to make sure that the 8 consecutive operator limit has not been exceeded.